Okay, in the last class we completed the Hilbert transform. Before starting the next class, that is properties of the Hilbert transform, let me go back to what we studied. We studied the Hilbert transform. We seen the equation of the Hilbert transform in the time domain as well as the frequency domain, and then we end up with two spectrums as you're seeing here. One is phase response and two responses on the phase response, and another is the amplitude response. Now question arises, if it is minus j, signum of f is equal to minus j for all the positive frequencies and plus j for all the negative frequencies. What I am telling is, you take minus 90 degree shift will be taken for all the positive frequencies, and plus 90 degree phase shift will be taken for all the negative frequencies. Why can't it take any other angles? So for answer for this is, I'll take that equation here. It is minus j signum of f is equal to, I'll just leave this 0 part. So minus j for f greater than 0 plus j for f less than 0. So what happened? What is this minus j means? It's imaginary. We know that it's e raised to, what is that? I'll just write like this equation, minus j signum of f is equal to e raised to j minus pi by 2 for f greater than 0, e raised to j plus pi by 2 for f less than 0. The question is why I wrote this? Answer for this is, if I take the e raised to minus j pi by 2, then what happens? It is cos minus pi by 2 plus j sine minus pi by 2. So what it is? Cos of minus theta is cos theta itself. So cos pi by 2. So this will be sine of minus theta is minus sine theta. So minus j sine pi by 2. And from the trigonometry we know that cos pi by 2, that is cos 90 is 0 and sine 90 is 1. So what is the answer? E raised to j minus pi by 2 is equal to minus j. So if I substitute angle theta as minus 90 or minus pi by 2, I am going to get it minus j. That's why I am telling, for all the positive frequencies, shift the signal by minus 90 degree. Similarly, if I take e raised to j plus pi by 2, so it's cos pi by 2 plus j sine pi by 2. So cos pi by 2 is 0 plus j sine by 2 is 1. So it will be j. So e raised to j plus pi by 2 is equal to j. So j, I can what it means? If for all negative frequencies it is plus j, that is nothing but plus 90 degree. Only for these angles the imaginary terms will be minus j and plus j. Rest all it will be different. That's why we are telling it is going to shift by minus 90 and this is going to shift by plus 90. So after completion of this, let me start with the properties of the Hilbert transform. So there are many properties present in the Hilbert transform, but for our studies we take only 3 properties which is there in our syllabus. The first one, a signal g of t and its Hilbert transform g cap of t have the same magnitude spectrum. Means the magnitude of g of f is equal to magnitude of g cap of f in the frequency domain. So what I will do is I'll just prove this. So what happens? We know that, what I know, my g det of g cap of t, if I apply the Fourier transform, what happens? It is g cap of f. So what is g cap of f? We already see in this equation. What is g cap of f? It is minus j signum of f into g of f. So if I take the magnitude of this is equal to magnitude of minus j signum of f into magnitude of g of f. This I will keep it as it is. What is the magnitude of the imagined term? It is 1. So what will remain here? Signum of f into g of f, the magnitude of this. Why? Because magnitude of imaginary term is 1. So after this, let me find out the magnitude of the signum of f. We know that. What is the spectrum of the signum of f? Signum of f spectrum, if you recall, it was like this. 1, this is minus 1, 0, this is f. Okay. So if I make a magnitude of this completely, if I make a magnitude of this, what happens? There are two values. There is 1, another one is minus 1. What is the magnitude of 1? It is 1 only. What is the magnitude of minus 1? It is also 1. So what will be the spectrum of this magnitude now? The magnitude spectrum of signum of f with respect to f is 1 for all the frequencies. So take this solution and put it in the above equation. So what happens? G cap of f magnitude is equal to, this will be 1, so magnitude of g of f. Hence proved. What they asked? They asked you to prove both the magnitude spectrums are equal. That I proved. So this completes the first property. Next comes the second property. If g of t is the Hilbert transform of g cap of t is the Hilbert transform of g of t, then the Hilbert transform of g cap of t is minus g of t. What it means? If the input signal is g of t, if I apply 2 times the Hilbert transform to that particular signal, then the output is minus g of t. That's what he is telling. So g of t is there. If I apply one Hilbert transform, I am going to get this, that is g cap of t. If I apply another Hilbert transform, we have to find out that whether it is minus g of t or no. So for that, I'll just draw this, already drawn this figure. So I'm going to go in the frequency domain. So instead of g of t, I have taken g of f. I am passing to one of the Hilbert transform system. What I'll get when I pass it, I'll get g cap of f. Again, I'll pass it to another Hilbert transform system. Now I have to prove that it is minus g of f. So together, these Hilbert transform, both the Hilbert transform I am just combined. I am going to name it as h dash of f, h prime of f. So now I have to prove that if I pass this through the h prime of f, I am going to get it minus g of f. So to do that, let me find what first is h prime of f. What is h prime of f? It is a multiplication of these two, h of f into h of f. So what is the h of f? It is minus j signum of f into minus j signum of f. So minus j into minus j, it is j square into signum square of f. Now what I say that minus j, we know it. What is this minus j? We know that sorry, j square is nothing but, imaginary square is nothing but -1. This we already know from the mathematics. Next, I am telling signum square of f is +1. Question is how? How it is +1? Let me take both the things. What is signum of f? +1 -1. So this is one signum function. Okay. This is multiplied with another signum function +1 -1. So what happens? Let's see. 1 into 1 signum square of f. 1 into 1 it is 1. Next, -1 into -1 1 itself. So if I multiply two signum functions, the result will be +1. So this I'll substitute here. What happens? So h prime of f is equal to, j square is -1, signum square of f is +1. So +1 into -1 is -1. So this is my h prime. Next, when I find of h prime, what is the answer of this? It is g of f into h prime of f is equal to what? We have to find out. So g of f into h prime of f is equal to what? So g of f as it is into h prime of f is -1. So it is nothing but minus g of f. Hence proved. What they have asked to prove? They have asked you to prove whether if I send this g of f through 2 Hilbert transform, the result is minus g of f. That I proved here. So this completes my second property. Third property, says that a signal g of t and its Hilbert transform g cap of t are orthogonal over entire time interval -infinity to +infinity. Orthogonal means that is integration of -infinity to +infinity. If I multiply these two and integrate with respect to t, then the result is, it should be equal to 0. So orthogonal means if signals are orthogonal means if the product and integration of those product is equal to 0, then I can say both the signals are orthogonal to each other. So I have to prove this. So let me start the proof. So for this, I'm going to take one generalized form of one well-known Pascal's well-known theorem. This you already seen in your mathematics, Pascal's theorem. What is that generalized form? It is integration of g of f into g cap of f conjugate a signal and a conjugate signal df. This is a generalized form of Pascal's theorem. So using this Pascal theorem, I'll try to prove this. So let me start. Integration -infinity to +infinity g of f as it is. It's a complex conjugate. It's a conjugate means what is g cap of f? What is g cap of f? My g cap of f is equal to minus j signum of f into g of f. So complex, the conjugate of this is, what happens? So minus will be plus, and g of f will be the complex of g of f. So I'll apply this here. So it will be into j signum of f into g complex of f df. So minus infinity to plus infinity. I'll combine these two. I will keep this as it is. So if I combine this two, it will be mod of g of f the whole square df. So we know that this function, the magnitude spectrum, is always an even function. What do you mean by even function? Even function means, I'll just show it here. If x of minus t is equal to x of t, then it is called as even function. And this already we seen in the signals and systems. The magnitude spectrum of any signal is an even function. And this one, the signum of f, is an odd function. This also we seen it. What do you mean by odd function? It is x of minus t is equal to minus of x of t. So this we seen in the signal system. We found out whether it is even or odd. We already seen this. This is a odd function. And multiplication of even and odd function is again odd function. And integration from plus into minus infinity of odd function is always 0. Is always 0. So these all things we already studied in the maths and the signal systems. So please recall these things. So what I can say now, this above equation, I can just minus infinity, that's term is equal to 0. Hence I proved that if both the g of t and g cap of t are orthogonal to each other. So this completes the properties of Hilbert transform. If you have any queries, please comment in the comment box of the YouTube, or you can just WhatsApp me. I already given the number in the first lecture. So once I complete this, let me start with I'll just take one simple example which was there in your textbook. Hilbert transform for low pass signal. This you know it. This is my low pass signal spectrum. That is from 0 to W, and the symmetry of this is this side. So what is the Hilbert transform? If I apply the Hilbert transform to this, what I will get? That we have to see it. So to do this, we know it. What we know? We already seen this point in the section. What do you see? If there is a positive, so we know that we've already seen it. If I have the Fourier transform, if I want to apply the Hilbert transform to this, for positive frequencies I have to multiply with a minus j, and for negative frequency I have to multiply with a plus j. So minus j means it is minus 90 degree, and for plus j means it is plus 90 degree. This we already seen in the first lecture. So what happens here? My g cap of f is equal to minus j into g of f for what? It is for all positive frequencies, and plus j into g of f for all negative frequency. 0 I will leave it. So what it indicates? For if the frequency is positive, then it has to be multiplied with a minus j, or it has to be shifted by minus 90 degree. So what happens with the spectrum now? So g cap of f, this is f. So minus j means the spectrum will be like this. Minus, previous it was in the positive part, now it will come in the negative part. So this is my this. So this is minus g of 0 and for the rest all frequencies, for the negative frequencies, it is plus j. So this will remains as it is. So this is plus g of 0. So for negative frequency from minus w to 0, it is plus j. The positive part remains as it is. But for the positive frequencies, the positive part will come in the negative part. So this is what the Hilbert transform of a low pass signal. So a simple example which was given in your textbook, I just solved it. Very simple. Just remember, if I want to find out the Hilbert transform of any signal, first convert into its equivalent Fourier transform, then multiply minus j to the positive frequencies plus j to the negative frequencies. You will get the spectrum of that or Hilbert transform of that signal. That's it in the frequency domain. So once I complete all the Hilbert transform and the properties of Hilbert transform, now question arises, the next topic comes as pre-envelope. And I already told about the real valued signal and complex valued signal. So pre-envelope, the question arises, what do you mean by pre-envelope? Why we need it? So the answer for this is, what if you already seen, what I'm just going to explain you already seen in your principles of communication system. What if I want only the positive part of the signal? Or for example, I have a band pass signal here. Okay, so this is my this is one part and this one is another part. Okay, what it was, you already seen this. This is upper side band and this one is lower side band. This is upper side band and this one is lower side band. Where you saw this? Exactly, this you already seen in the SSP single side band modulation. So the question arises, how can I extract only this upper side band or the lower side band? Or in other words, if I take a low pass signal, how can I extract only the positive frequency part? How can I extract only the negative frequency part? Or another question arises, what if I apply the Hilbert transform to this? What I will get? So if I want a part of a signal to be extracted, then I'm going to go for this pre-envelope concept. So if I want to go for the pre-envelope concept, I need to apply the Hilbert transform to the band pass signal. That's why we learned the Hilbert transform. Now we are going for the pre-envelope concept, where I can just extract a part of a signal. In this signal, I can extract the positive part or negative part, or upper side band or a lower side band. So this concept will be explained in the pre-envelope. So what I told, what if I want only the one of the side bands? I'll just write it here. So upper side band and lower side band. Similarly, this is lower side band and this one is upper side band. This already seen in the SSB modulation. And what if I want only the positive frequencies or only the negative frequencies? Then I'm going to go for the pre-envelope concept, and to get what exactly we are going to do is in this, we will see it. Again, we are going to take a help of Hilbert transform in this concept. So let me start this. So Hilbert transform, I told you that this you are going to use it. So let me define one equation. The pre-envelope of g of t is defined as g plus of t is equal to g of t plus j into g cap of t. This I will call it as 1. I just define this equation. And here this part is pre-envelope for positive frequencies, and this is my real part, and this one is imaginary part. So remember this is plus, but that means it is a pre-envelope of positive frequency. That means I want to extract the positive part now. And this one is g of t is a real part and g cap of t is a imaginary part. Now apply the Fourier transform to this above equation. That is Fourier transform of g plus of f is equal to g plus of f. So g plus of t is equal to is nothing but g plus of f. Then we can write equation 1 as, what you can write? G plus of t is nothing but g plus of f. G of t is nothing but g of f plus j as it is, g cap of t is nothing but g cap of f. Just wrote in the frequency domain. So g of f as it is, j as it is. What is g cap of f? This we already seen. It is minus j signum of f into g of f. It is from the Hilbert transform. Next, take this out. Next, j into j, it is j square. So j into j is a j square. So plus into minus, minus. So it will be minus j square. What is j square? I already told. It's a imaginary square is nothing but minus 1. Minus 1 to minus 1, it is plus 1. So that's why what is remaining? G of f as it is. So this j part will go off and it will be equal to 1. We seen it. Signum of f as it is, g of f as it is. I call this equation as 2. Now so we know the equation signum of f. What is signum of f? 1 for all positive frequencies, 0 for 0, and minus 1 for all negative frequencies. Let me substitute this signum of f in the equation number 2. So this I'll keep it as it is. Now I'm going to substitute only the signum of f. So for f greater than 0, that is for positive frequencies, g of f plus, I'll just, for your sake, I'll just write the equation here. So signum of f into g cap, sorry, it is g of f again. So now I'm just going to substitute this signum of f here. So g of f as it is plus 1. What is for positive frequency? What is the signum of f? This is plus 1. So 1 into g of f. The g of f plus g of f is number 2 g of f. Now for f is equal to 0, substitute f is equal to 0 here. G of f is equal to 0. So if I substitute, it will be g of 0 plus, say what is the signum of f for f is equal to 0? It is 0. So it is 0 into again g of 0. 0 into g of 0 is 0 plus g of 0 is g of 0. Now coming to the last one, that is for f less than 0, that is for negative frequencies. My g of f was there, now it is minus f because I am taking the negative frequencies, plus what is the signum function for the negative frequency? It is minus 1 into again g of minus f. As it is a odd function, what happens? My g of minus f is nothing but minus g of f plus minus 1 as it is. Again g of minus f is nothing but minus g of f. Now minus into minus plus. So g of f, this minus g of f as it is, both get cancelled, it will be 0. So what it indicates? If I apply the pre-envelope for a signal g of t which has both the positive part and negative part, or both the frequency spectrum for both positive frequency as a negative frequency will reduced to this part, is a positive pre-envelope For positive frequency it is 2g of f. For 0 it is g of 0. For negative frequency it will be 0. So what I can say that the negative part is completely gone, or negative frequencies are completely 0. What I am getting from the pre-envelope is I'm getting only the positive part. So this is what I wanted to do. This is what I did it using the pre-envelope concept. Next, symmetrically, to determine the pre-envelope of the negative frequencies, just what was the pre-envelope of the positive frequency? It is g plus of t is equal to g of t plus j of g cap of t. For negative frequency it is g minus of t, g of t minus j, g cap of t. That equation I just wrote it here. Call this equation as 4. Here g plus of t and g minus of t are the complex conjugate of each other. This we already seen it. So that's what. So negative part and the positive part both are complex conjugate to each other. Taking Fourier transform for foreign solving. If I do the same what I just did the mathematics here, if I do the same mathematics, if you want you can just do it as an exercise for you. Just simplify as above, which is shown here. Just do it for this also. I'm going to get it as g of minus f is equal to 0 for positive frequencies. For f is equal to 0, it is g of 0. For negative frequency, it is 2g of f. So once I seen this, by this what I can say that, by this we can say that we can get positive and negative frequency content of a signal g of t, which is a bandpass signal, by applying the Hilbert transform or pre-envelope. So this is what the pre-envelope says. Now before ending up with this, let me draw the diagram. So the diagram, what I just given the equation here, my g plus of f and g minus of f, I'm just going to draw the diagram for both of them. So my g plus of f is equal to, it is 2g of f for f greater than 0, g of 0 for f is equal to 0, 0 for f less than 0. So how it will be? So what is my signal? I will consider my g of f as this, a low pass signal. Let me consider g of f as this. So if I apply the pre-envelope on this, if I apply the pre-envelope, what I will get? I will get, if I have the positive pre-envelope, what I will get? That is g plus of f is equal to, what is it? For positive frequency it is 2g of f. For negative frequency it is 0. So for 0 it is g of 0. If I apply the negative pre-envelope, for the negative pre-envelope, as we seen this equation, it will be, for negative frequencies it will be 2g of 0. So this is my spectrum of negative pre-envelope, and for positive frequency it is 0. So this completes my second lectures. In the next lecture we are going to see how can I extract the positive frequencies and negative frequencies, or how can I convert the band pass signal to the low pass signal, or if a signal is given, how can I find its pre-envelopes. In the next class we're going to see that, and then we're going to shifting our class to the complex envelope, where we're going to take the complex valued signal. And I already explained the complex valued signal. What do you mean by complex valued signal? So I will discuss all those things in the next class. Hope you understood this. If you have any queries, please tell me and comment in YouTube. Thank you.